Okay, so let's start today's class with the syllabus discussed. I hope like no one has any problems, but if you have any, please contact me, email me, and I can tell you that. I do not remember if I told this before, but attendance will have 5%. The concept map, so we tried to start with the concept map, but we couldn't, so let's try with the concept map today. So geochemistry has a geology part to it and a chemistry part to it. Whatever comes on the later half of any name, that is the more important part, right? So it's like if bluish pink is a color, I don't know if that exists, but pink will be the more, like the more, that will have more weightage. So geochemistry is not chemical geology. So it will obviously start with the concepts of chemistry and grow on that, and the geo part will be the application part of the chemistry, okay? So we'll start with module 1, which is fundamentals of chemistry. The fundamentals will include general phase changes, or like phase and the changes or interconnectedness of the different phases. So you have a solid phase, liquid phase. What happens when you go, what is it called when solid goes to liquid? Simple things like that. Why does it happen? And that's where we will discuss today the concept of latent heat. This has very important implications because it has two very difficult words, heat and latent. Heat is not that obvious. There's a difference between heat and temperature. We'll like briefly discuss it. We'll also discuss temperature and pressure, these kinds of like important concepts that keeps on coming time and time and again. So fundamentals will have phase and changes, and then we will go to atomic structure. And atomic structure is important because any reaction that happens, we can tie it down to the atomic structure, anything that happens. And in atomic structure, we mean electronic configuration. So you might have some idea about the KLM, the 2n square rule, or the SPDF, or battle. So show of hands, like how many of you know to do the electronic configuration using SPDF? You don't? That's very important. So once we do that, a lot of chemistry will become clear. So electronic structure, or electronic configuration, absolutely critical in understanding chemistry. And if you understand the chemistry down to the basics, everything should, in theory, become clearer. That's what we will study in the atomic structure. So there are fundamentals, and then we will try to understand a little bit about isotopes. And there are more. There are isotones, there are isobars, and the list is endless probably. But the most important thing would be understanding the concept of isotopes, because there exists another module that this will get interconnected, and in your concept maps, when you draw it using Illustrator or whatever, this is how you have to connect this module to two different modules. The two different modules to which isotopes will get connected is the isotope geochemistry module. Okay? Now there are two types of isotopes. There are radiogenic isotopes. Can you guess what radiogenic means? Just a random guess. Come on.
It's radioactive.
Yes, it's radioactive. So it will decay, right? And why does anything do anything? Why is it decaying? Why are you in the class? Because you're required to, but in general, why are you in the class? To learn, but why? Is it important?
Yes, for our jobs, hopefully.
And why are you going to get, like, why do you need the jobs? To have a stable life, right? Like, stable source of income, stable life. So everything in this world is happening for stability. There are some people and some things that happen for instability, but that's very rare. Everything happens for stability. Everyone wants stability. Everyone wants to achieve stability. And how do you reach stability?
They happen.
Huh? For anything to reach stability, what was the idea that I told yesterday? For anything to be stable, they have to do what? It's something related to energy. What they have to do to gain stability? They have to release energy, or they have to become less energetic. So if you release energy, you lose energy, you become more stable. So all these things will come together. Like everything is trying to release energy to become more stable. Okay? So there are radiogenic isotopes. So a lot of this, so there is a course that is going on, I think Mike Cannon in our department, he's teaching this course that is called Geochronology and Tectonics, probably. So what is geochronology? So geo and chronology, chron means time. So when we say the Earth is 4.56 billion years old, how do you know it? I was once in a very heated debate with someone, and he's like, how do you know it? It's okay, we know it because there is radiogenic isotope. We fairly understand how things decay, and that thing takes some time. So this connects to another course, which is geochronology. We'll get to know the basics of geochronology because that will help you understand the age of Earth. Because the age of Earth is known only through this. Like there is no other, there are estimates through geological processes, but the way to actually know the age of anything is through rocks. Also, you might have heard, or might not have heard, we try and estimate the outcrops and the ages on different kinds of planets. For Mars, there are like on Earth we have Jurassic ages and Triassic ages or Archean, things like that. How do you know? So you take the rocks, do geochronology on them through radiogenic isotope systems like uranium. There is argon. So there are many radiogenic isotope systems, lead isotopes. We study those and we get the ages of those rocks. But for some planets, we don't have the direct evidences of the rocks, and we'll learn about those things in planetary geology, and Alan teaches that course. So, but to know the actual age, you need radiogenic isotope systems, right? Geochronology and all those things. There are also stable isotopes. So this is like lead, uranium, blah, 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 stable isotopes. There are stable isotopes like sulfur has a stable isotope system. Okay, oxygen has stable isotopes. Hydrogen has stable, so there are many stable isotope systems. So why do we study stable isotopes? We study stable isotopes because they are proxies for various different kinds of geological processes that might have occurred on Earth or on a different planet in the past. We cannot go back in time, but we can look at different stable isotopes and how these different, and they will tell us something. They might tell us about the Ice Age. The Ice Age might have happened. They might tell us about how there was a carbonate precipitation at one particular time in the history. So these are different things. So stable isotopes are used as proxies for geological processes. Okay, on Earth, any different planet. So that is why geochemistry, isotope geochemistry is important. We have to understand isotopes, basic ideas, to get to isotope geochemistry. Okay, so this is how it is getting connected there. So somehow this is connected to that. So after the fundamentals, we'll also try to understand, okay, now, radiogenic. Can anyone tell when radiogenic isotopes decay, they follow a certain kinetic law? Have you heard about this? Like which law it follows? Is the first, the second, the zero, third? Have any idea about the decaying part of the radiogenic isotopes? You will not know this unless you study kinetics.
It's like, I think, the second or the third law, one of those two. I don't remember.
Okay.
I'm just not sure which one.
I think you might be getting confused with thermodynamics.
Probably.
Probably, right?
I remember like a section in chemistry when they had like, it was like A equals, and it was like, oh, you can make it to like the half-life equation.
Yes, it's the half-life. So all these so taking a step back, anything can have a half-life. Radiogenic isotopes follow first law, first order kinetics. So this thing is very much tied to another branch called kinetics. So this is another, so this is one module, this is another, this is another. And we will study kinetics with thermodynamics. So thermodynamics will tell us whether a process is feasible or not, whether something will happen or not happen, theoretically, energetically. So this is the part where we'll study about the energetics. Call it energetics. Because as I said, everything wants to decrease, everything wants to gain stability. To gain stability, you need to decrease your energy. And thermodynamics will tell us whether a process is feasible or not feasible based on, not the half-life. Half-life is one of the ways in doing it. But based on if the energy is decreasing, it's feasible. If the energy is increasing, it is not feasible. And if the energy is equal, what is that? You might have a...
Stable?
It is a form of stability, but there's a chemical, yes, right? So when energy is decreasing, decreasing, increasing, and zero. So when it is decreasing, it's actually feasible, not feasible, and this is equilibrium. This is another huge topic, equilibrium. So we'll also learn about equilibrium. So see, like you study about, so all these things are connected. These are not islands. These are all like the freeways in San Antonio. Everything is connected. And you have to know how these things are connected to get a bigger idea about the whole concepts, right? So equilibrium. Now, if you are taking petrology or mineralogy, things like that, equilibrium becomes important. You might get phase equilibrium. So again, the concept of phase will come here. You have to understand what is a phase. Have you seen the diagrams like these, like the football-shaped diagrams, right? This is like the phase equilibrium and things like that that we'll study here, okay? So you can study equilibrium in the solid state using those diagrams, and there could be, so the concepts of eutectic, peritectic, equilibrium, solidus, liquidus, very much about petrology. We'll try to get the basics from here. Try to understand what happens when you decrease the temperature, things like that, simple concepts. Then we'll also learn about the liquids. This becomes really important because there is a field. So this will be petrology. It will relate to petrology. This, we will not study petrology here. Petrology is a different course, and I'm not going to like teach what Alan is going to teach. This is the field of aqueous geochem. So you see how these names are coming up? We are teaching geochemistry, and then you're studying isotope geochemistry. So the isotope part is being added. That is one module. Aqueous geochemistry. So the aqueous part will be added to that, right? So in here, we'll study all the geochemistry that is happening in the liquid phase. And why do we care? Why do we care? Why do you care personally? Do you care? Would you want to learn about aqueous geochemistry?
I'm not completely sure. It's not really.
Don't think of it as like an educational question.
Okay, that's what I was thinking of this.
Philosophical. Why would you care about something happening in liquid? Aqueous, mediums, things like that. Why would you care? Or do you?
I mean, yes, but like,
Why would someone care?
just like blanking
For the health
right
of the
now.
people.
Sorry?
For the health of the people,
And why is that?
such as like carbonate dissolution in the Edwards aquifer, or looking at like a saline water zone that we have.
You talked about CO2 and how the CO2 plus H2O things will happen. What more?
Most of the planet is water.
That's what? 70%. So if we care about the planet, we need to understand what 70% of the surface is doing, right? And it is not just an isolated system. It is connected to the atmosphere, right? So the liquid is connected to the atmosphere. It is also connected to the lithosphere, right? Now, interestingly, there is this thing. So have you heard about? So there are so many ways. We are 70% water, so that's why we drink water. That's why we should. So you are blanking out. I get it. I'm sorry to put you in this, but the thing is, you would care if your liquid, this thing, had lead in it, or arsenic in it. In Bangladesh, there's a problem of waters containing a lot of arsenic. What do you do with that? Now, if you were living close to a radiogenic dumping facility, you would care, because if you're dumping the radiogenic things and the groundwater is interacting with that, and that is what you're drinking, you will care. Jinu, why do you care? I know you are in that aqueous geochemistry thing.
Oh, yeah. I think because the liquid, it can move, it can flow in the soil, underground, it can move.
Right. Liquid moves, right? Like, so if you have uranium, or if you have arsenic, or if you have some contaminant, it will dissolve it and move. Now, a huge part of like what aqueous geochemistry does is environmental geochemistry. So based on the simple ideas that we'll pick up from this, you can apply to aqueous geochemistry. Someone said about planet, I think Courtney did. A lot of planetary geochemistry is actually aqueous geochemistry. Because if we want to study life on Mars, water is one of the very important aspects that we need to understand. What was the water back then? So Mars has like no visible forms of liquid water on the surface right now, but it had liquid water in the past. We know it because we can see geomorphological features. We can see river channels, outflow channels, things like that on the surface. We have gullies. We have some liquid water activity right now, even. We call it recurring slope lineae and things like that. One of my, I know like some of my friends are doing these kinds of research that is there. But also there are minerals that tell us that there was some type of liquid that existed on Mars. So from the solids that can only precipitate in liquid water, there is a mineral called jarosite, which was discovered, which was predicted to be found on Mars by Roger Burns. He was in Caltech or MIT. So he predicted that on Mars you will have this particular mineral. And then when the Opportunity rover landed in Endeavour crater, Meridiani Planum, there is a place, it actually found jarosite. And when you see jarosite, you immediately know what kind of liquid existed that precipitated the jarosite. So there comes mineralogy, planetary geochemistry, aqueous geochemistry, all getting warped up together, which you might show in your concept maps, how these things are getting together. Now, planetary geochemistry is another thing. Now this basically will engulf anything and everything. So this can engulf solids because planets have solids. This can engulf liquid because we are trying to understand liquid. This will also be tied to astrobiology because if we are trying to understand life and how life formed on Mars, we need to understand so Carl Sagan called us water chauvinists and carbon chauvinists because all life forms as we know it are made up of carbon and they need liquid water. Every life form that ever existed, ever found on Earth is that. It might not be true for other planets, but as we know it, this is the case, okay? So planetary geochemistry can be connected basically to anything. And how it gets connected, it would be interesting to see how you see it connected. So basically how I see this connected with geochemistry is through aqueous geochemistry because that's what I do. I do experiments in aqueous systems to understand. So I take minerals and I'm trying to understand how did that mineral form. So if you have jarosite, can you tell something about the pH, which we'll also understand, which we'll also learn in here. What is pH? What does that mean? What is acidity? Another important thing is EH, or the oxidation potentials of the systems. How oxygen rich that thing is. How can you determine the oxidation potential when there is no oxygen? So that can also come in, and we'll learn that in aqueous geochemistry. This will also engulf a lot of radiogenic, because if we are trying to find out what has happened, what's the age of different planets or meteorites, we need radiogenic isotopes. So you get meteorites, you directly age them because you need to understand how did we know that the age of the solar system is 4.56. The age of these Earth and all these different planets are 4.56. All Earth, Moon, all these things have almost equal ages. How do we know that? Radiogenic. So planetary geochemistry, again, connected to radiogenic systems. Okay. There is also another field called trace element geochemistry that Brian, who was there the other day, he is learning. These are those elements which are very little in concentration. So a lot of the Earth is made up of oxygen, aluminium, magnesium, silicon, and all this kind of stuff. These are the major elements. Then there will be minor elements. Then there will be trace elements. We'll study all those things too. So this is a very interesting. So all the magic, many of the very interesting things that happen and that we know that happen comes from the trace. The magic happens in the trace. It doesn't happen in the bulk. All the magic will happen when we have very little, and there will be subtle changes. And these kinds of things we came to know only recently, maybe 50 years ago, because of instrumentation. We did not have the instrumentation to go to that final level. Right, 200 years ago, we couldn't understand how europium can preferentially go into plagioclase. So europium is a trace element, and it can also act as a proxy for various geological processes. So you take a rock, you study the trace elements, and you can tell a lot about where did it come from. How did it, based on the partitioning of these trace elements, a lot of the ideas can come out from that. So you see, like, all this geochemistry is there, and we have to map these things. You get a feel for this first, to get a bigger idea, and then we'll again come back to this, and each of you will have your own picture of geochemistry. Okay? All right. Now, let's move on to some of these concepts, phase changes and temperature and pressure and these kinds of things. Okay? I'll just reset the camera.